A few of you probably read the title of this and already know where this is going. Uh, there is already a WebAssembly channel in Slack, and what's interesting is that there's a disproportionate number of CS11 students in there, which I find interesting. But anyways, so maybe some of you have a bit of an idea of where this is going already, but I think for most of you, probably not. Or just very curious. Okay, I think when I actually present in Keynote, it uses like both my screens because the other screen, it like tells me what's the next slide that's coming up and stuff. So I don't think I'll be able to see Slack as we're doing this. So apologies for that. I guess questions will. I mean, you can type questions in Slack. I'll just won't get to them until the end. All right, cool. So let's start for reals now. So for this morning, I thought I would introduce WebAssembly and kind of talk a little bit about what that is, what it means, and I guess kind of why it's cool or why I think it's cool. So yeah, what is WebAssembly? First question on most people's mind, I would imagine. And I think this quote summarizes it pretty succinctly. But basically, WebAssembly is a way of taking code written in programming languages other than JavaScript and running that code in the browser. It's a quote by Lynn Clark. She is kind of the face of like developer relations at Mozilla, where they company that behind Firefox, and that's because WebAssembly is this kind of huge project that's being undertaken by all the major browser vendors. So there's a lot of people who work on Google Chrome are also working on WebAssembly. People Mozilla, Safari, Microsoft Edge, all these like major browsers are working to standardize around a spec for WebAssembly so that all of them have support for it. So so far at this point, I think kind of the major winners in terms of languages are what you see here. So languages like Rust, C++, C, and Go to a little bit of a lesser extent. So really kind of Rust, C++, and C, I would say, are kind of the most ahead of the pack when it comes to being able to leverage WebAssembly the most. And we'll get into why in a second. But basically, it's Rust, C++, and C are basically kind of the languages that can take advantage of what WebAssembly offers the most. That's not to say other languages cannot. So again, Go does to a lesser extent, and I'll get into why in a bit. But that doesn't rule out languages like Python, Java, C#. Like those languages too can definitely benefit from WebAssembly. But because WebAssembly is still a very new technology and there's a lot of things that still need to be implemented into the specification, those other languages need to wait on certain features for those to be implemented in WebAssembly before they can kind of really take full advantage of it. Anyways, let's get into a bit about how it works. So historically, browsers have only been able to run JS. Browser engines would just be able to read and interpret JS code. I think we're all pretty aware and familiar of that fact. And now what all the major browser vendors are doing is they are enabling or adding on additional functionality into the browser engines to be able to read and interpret this new file format called WASM, short for WebAssembly. And the difference with WebAssembly compared to JS is that JS, as we all know, is a programming language that humans write. Like you guys write that a lot. You guys are probably writing it right now for your projects. WASM is a bit different because WASM is what's called a compiler target. So humans don't typically write WASM. Instead, languages will be compiled to WASM, right? So typically languages like Rust, C++, Go, these sorts of compiled languages, typically they compile down to machine bytecode to be run natively on your machine. Like when we compile a C executable, right? That gets compiled into bytecode that is appropriate for the operating system and the architecture that your machine is running on, right? So then we can go and execute the executable on our machine. So WASM is different in that it's basically a machine. It's a custom bytecode type that is specifically designed to be run in the browser, versus typically what is typically outputted by compilers, which is machine code that's meant to be run on natively on your machine. Right. So again, now all the browsers are adding support for this WASM file format, and then all these compiled languages and also non-compiled languages can also take advantage of this. But again, compiled languages as of right now are kind of the main winners so far. They can augment the compilers so that the compilers can also output this WASM file format instead of just native machine bytecode. And that's basically how that works at a kind of 30,000 foot level. So basically, we're going to get a lot more diversity in terms of what sorts of languages and tools we can use on the web instead of just JavaScript. So that's kind of one of the main benefits of WebAssembly technology. Let's talk about some other ones. Chief off the bat is also that WebAssembly is more performant than JS. And this is kind of, well, let's take a little bit of a look at that. But kind of the main reason why, if I were to summarize it into kind of one reason why this is the case, is that, again, it goes back to the fact that JS is actually designed to be written by a human, whereas WebAssembly is not. Again, it's designed as a compiler target for other languages to be compiled into. And so you actually get a bunch of advantages that way, most notably that, the WebAssembly format can be optimized much more for machine readability. But anyway, let's break it down and talk a bit about what actually happens when you run JS code in a browser. Right. So the very first thing that needs to happen, and this is a consequence of the fact that, again, JavaScript is an interpreted language, is that the code needs to be parsed into a special data structure called an abstract syntax tree, which is a variant of a tree data structure. But I'm not going to go more into it than that. But basically, the abstract syntax tree represents your written code in a structure that can then be interpreted by a compiler. A compiler is going to see that and then basically compile it. So once that code's been parsed into an abstract syntax tree, it needs to be initially compiled and optimized. And as we'll see in a second, there are actually multiple optimization steps. And kind of in this first optimization step, the JIT, and JIT stands for just-in-time compiler, and that's what the compiler that compiles JavaScript code in browser engines is referred to as, is a just-in-time compiler. But in order to make optimizations to that code, it makes a lot of initial assumptions about it. And so also the fact that different versions of the same JavaScript code actually need to be compiled. And this is because JavaScript is not a typed language. So the fact that JavaScript is not a typed language, I mean, that's nice for the developer in the sense that we can be a little bit loose with our code and not have to specify types. But under the hood, what that means when you're trying to compile JavaScript code is your machine still needs types in order to work with your code. And so what it actually does is, when you don't specify a type in your code, it basically needs to compile multiple versions of that code that'll work with any type that could be sent in through your code. So that all needs to happen. Next up, because of the fact that the compiler, again, it makes some initial assumptions about it in order to optimize your code on the first pass, you can imagine it's prone to getting some of those assumptions incorrect. So actually what happens is your JavaScript code, as it's being executed, goes through multiple rounds of re-optimization. And what that basically means is when the compiler realizes it made an incorrect assumption, it needs to correct for that. So the code needs to be unoptimized, and then it needs to go through more cycles to figure out what is the correct way to actually optimize this now. And that's what it does when it's re-optimizing your code. So if, as your code executes, it does get more and more optimized, but it takes time for that to happen as your code is executing. Of course, the code needs to be actually executed, needs to get actually run. And then, of course, garbage collection needs to happen. Resources need to get cleaned up, and so on and so forth. For you visual folks out there, you might think of it more like this. Maybe this is a bit more clear. Right. So again, at the top, in the top left, you have your JS program. It goes and gets parsed into an abstract syntax tree. This diagram says that abstract syntax tree gets sent to an unoptimized compiler, which, sure, I can see that. We're calling that first initial pass the unoptimized compile step. But there's some slight difference in interpretation here between what I wrote down in the previous bullets and this graphic here, but it's okay. So that gets compiled to some bytecode, and then here says it gets put through the turbofan compiler. Not really sure what that is, but I'll take its word for it. And that compiler is what spits out the compiled and optimized code to then be executed. As a little bit of foreshadowing, we see at the bottom, the WASM binary kind of just comes in at the bottom, which we'll talk about in a second. We'll, again, go through the steps for how WebAssembly actually gets run and executed in the browser as well. Another thing is that all these steps I just laid out, they don't happen in a sequential order. And so basically what this little graphic here means is that, so P stands for parsing, C plus O stands for compiling and optimizing, E is executing, R is re-optimizing, and G is garbage collection. But basically, don't worry too much about that. Basically, all I'm trying to say with this graphic is that these different steps that we talked about, that we just outlined, they happen all over the place, right? So they're not happening in sequence. Some parsing will happen, some compiling and optimization will happen, some execution will happen, and then maybe it'll like go back to parsing more code as it comes in. Maybe the garbage collector will run for a bit, and then more parsing, more executing, etc. Is basically all I'm trying to say, is that all these steps that we just talked about do not happen in sequence. And so one of the other major downsides of JavaScript code in the browser is that its performance is extremely unpredictable, right? Due to the fact that, for example, we don't have complete control over when the garbage collector runs, for example, and for how long it needs to run. It'll just run for as long as it needs to run until it's cleaned up all the resources when it decides to run. And again, us as developers, we don't have control over that. So, and of course, due to a lot of other factors as well, JavaScript code is known to be unpredictable in terms of its performance. Anyways, from there, let's talk about what needs to happen when we run WebAssembly code. So again, because WebAssembly code doesn't actually need to it's not interpreted, right? So WebAssembly is all going to be compiled from whatever language you choose to run, be it Rust, C, Go, whatever, that code will all be compiled ahead of time. So when it actually gets to the browser, we don't need to do that parsing step of parsing the code into an abstract syntax tree on the browser side. That basically already happened on the developer's end because, again, just like how we have to compile C code, it's kind of the same thing, right? So like basically in C, one of the steps for when you go and compile C code is that's basically when the parsing happens is in the compile step. So a lot of that work basically gets front loaded, and so the browser doesn't have to handle it. There's another compile and optimize compilation optimization step, but a lot of those optimizations also already happened in the initial compile step, and so there's not nearly as much optimization that needs to happen when that code actually gets to the browser. Plus, a lot of WebAssembly language, a lot of languages that target WebAssembly, again, like Rust, C, C++, Go, etc. These are all statically, strongly typed languages that have type specifications built into the code. And so again, that's not something then that WebAssembly needs to, or the browser needs to deal with when it comes to optimizing the code. This is the basically saying there's no need to do reoptimizations, right? So this kind of ties in with the previous bullet, but again, because of the fact that the code is already compiled, doesn't need to be interpreted on the fly, the compiler doesn't need to do nearly as many guess and checks of its optimizations to ensure that any of the initial assumptions it made are correct or not. So reoptimizations and the first kind of optimization step, maybe you can think of as they're kind of rolled into one, and that step doesn't really take nearly as long as what needs to happen with JavaScript. Of course, the code does still need to be executed. What's interesting to note is the actual execution step, and they've done like benchmarks of this. If we just actually compare just the execution steps of JavaScript and WebAssembly, those are actually rather comparable. So in terms, again, just in terms of plain execution, WebAssembly actually is not much faster than JavaScript. But if you take all these other time saves that we've been talking about here into consideration, you can imagine that WebAssembly starts executing a lot faster, and so it gets more of like a head start compared to when JavaScript starts executing. And so, yeah, it comes out, it ends up being faster on the whole. And then another thing is that garbage collection is not actually supported in WebAssembly code. So garbage collection doesn't actually happen. And this is a big reason why languages like Java, like Python, and languages like that don't see as many benefits from WebAssembly right now as languages like Rust, C, and C++. So I said earlier that Go was also a winner to a bit of a lesser extent. And that's because Go itself is still a garbage collected language, right? So we know that with, in our case, because we've worked with C, we know that in C, we perform all of the garbage collection ourselves. That's all spelled out in the code already. There doesn't need to be any sort of garbage collection system like there is with Python and JS that runs in the background to actually clean up and free memory on your behalf, right? It's not that garbage collection doesn't happen. It's that garbage collection is explicitly specified or spelled out by the developer as to when it needs to actually happen and how it happens. Rust has a very different way of handling garbage collection. I'm not going to get into that. That's kind of a deep rabbit hole. But suffice it to say that Rust basically handles its own garbage collection as well. And so Go does have a garbage collector. And basically what needs to happen when you compile Go to WebAssembly is that in the process of compiling Go code to WebAssembly, basically the entire garbage collection system that's built into Go also needs to get compiled to WebAssembly. So that basically just gets brought right along and translated into WebAssembly code so that Go does have a garbage collection system available to it. But basically what that means is then that so for example, when you compile Rust, C, or C++ code to WebAssembly, those WebAssembly files are going to be smaller generally than Go code that gets compiled to WebAssembly, because again, with Go code that is compiled to WebAssembly, that inherently needs to include the garbage collection system right in that code. And so that would be the same with like Python and Java and JavaScript as well, right? So with those languages, Python certainly is garbage collected, same with Java, same with JavaScript. But also the fact that they don't, Python, JS, so Python and JS are not strongly typed. And so WebAssembly right now mostly only has support for those typed languages. So here is an interesting benchmark. So I think a lot of us have, when we were working with JavaScript, have probably worked with a library called source maps, right? So what source maps are they, because right now when you run JavaScript code, it gets, so you write your JavaScript code and then you package it up, right, via like Webpack or something like that, and that will bundle all your code and mangle it up and put it in this kind of format that's not easily human readable, right? So that happens a lot with JavaScript code that you then want to execute on a browser, like when you deploy it, or even when you just run it locally in a browser. And so source maps are what allow you to basically map from that mangled JavaScript, and it'll point to, like when an error happens in your mangled JavaScript, that will point to the actual line in your human readable code, right? So I think a lot of us have worked with source maps. It's definitely kind of like a really, well, it certainly has a lot of downloads on NPM, for example. But yeah, super useful stuff, right? Because otherwise you'd be looking at error messages that just pointed to the line in the mangled version of the JavaScript. And it'd be a lot harder to kind of make sense of where the error was actually coming from in your JavaScript code. And so that's basically what source maps provides you, right? So what's interesting then is that this benchmark came from the team that maintains the source map library. So actually what they ended up doing is they basically ported most of the heavy calculation and logic of the source map library, wrote it in Rust, and compiled that to WebAssembly. And then compared the performance of the old version, which was all written in JavaScript, and the new version that leverages WebAssembly. And so the way you can kind of interpret this graph is the results. So we can see at the bottom, there's a timestamp for JavaScript in Chrome and WebAssembly in Chrome. So they did a bunch of these benchmarks across different browsers, running source map, the old version of the source map library against the new version. So we see timing benchmarks. So for example, in the first, in Chrome, we see that on average it took maybe about 1,500 milliseconds for the source map library to execute. And specifically, this was measuring how long it took for when you set a breakpoint, right? So you set a breakpoint in your browser, then how long it takes for the source map library to run once it's encountered that breakpoint. So within that space of time, it needed to basically pull apart your mangled JavaScript, figure out where the error was coming from, and point to that in your human readable version of JavaScript. It's basically what they were benchmarking. And we see the WebAssembly version is closer to 1,000 milliseconds down in the second column, and of course other timings as well. But apart from the actual timings, and of course we can see that WebAssembly is significantly faster. Also notice that the spread of the JavaScript versions, there's a lot more spread with those, right? And we talked, I alluded to this a little bit earlier in that with JavaScript code, I said that JavaScript code performance is way less predictable. And that's basically what we're seeing here, right? We're seeing that JavaScript code can have, there could be a lot of standard deviation. There could be a large standard deviation in the performance of the JavaScript code, right? If you just look at the benchmark for Firefox of JavaScript in Firefox, that ranges from like 3,500 milliseconds to, I don't know, about 2,700, right? That's a huge spread. Okay, and then conversely, we see with the WebAssembly benchmarks, those are all, for the most part, pretty close together. So WebAssembly performance is not only faster, but again, it's also a lot more predictable. And again, that's by virtue of the fact that, due to the fact that, with, for example, again, in like Rust, C, C++, you, the developer, control when memory is freed. You know exactly when garbage collection is happening. And just again, with lower level languages, you just have a lot more control over how memory is being handled, right? We don't need to go through the JavaScript runtime in order for that to happen, right? Because when we're writing code in JavaScript, we're basically leaving all of the memory control and allocation and stuff like that up to the JavaScript runtime. And it basically has a huge amount of freedom in deciding how it wants to do that and when it wants to run. And that's why we see a lot of variance in these benchmarks. And then as another small point, it also turns out that WASM files are typically also smaller in size than JS files. So we didn't even talk about the size of the files and how that, because JavaScript typically has larger file sizes than code compiled to WebAssembly, that it actually, it takes more time to also just download JS files compared to WASM files. And so that's another metric in favor of WebAssembly, in that the code is going to get downloaded into a user's browser a lot faster. Well, maybe not a lot faster, but definitely faster, just due to the smaller file sizes. Okay, so let's talk a bit then about what are some of the implications of this technology, and maybe what have some people been doing with it already. So one big implication, and again, another thing we kind of alluded to when I was talking about the source map example, is that a lot of libraries, a lot of JavaScript libraries, stand to see a lot of performance gains by porting parts of their applications into WebAssembly, right? Again, those parts of a library that perform the heaviest calculations and stuff like that, it makes a lot of sense to go and translate that code into WebAssembly code in whatever language the library writers choose. So of course, again, they can go with Go, they can go with Rust, C, C++, whatever. That choice is totally up to them, and compile it all to WebAssembly and see the resulting performance gains. So one of the things that I think is actually in the works right now is that React is actually in the middle of porting the DOM reconciliation algorithm from JavaScript to WebAssembly. And again, that's the one where the virtual DOM nodes get swapped in and out when you go and re-render. So it makes a lot of sense to write that in WebAssembly for performance gains, to see that algorithm perform much more quickly. Another major implication is that popular desktop applications, like, for example, Photoshop, Premiere, or even like a lot of like game engines like Unity, those have all historically been implemented in C and C++ as native desktop applications. But now, with the advent of WebAssembly, those applications can literally all be ported to the web. And then you'd be able to like do Photoshop from your phone or tablet. Well, I mean, you can already do it from a tablet, but I mean like from your tablet in a web browser. Another example is that Autodesk, which makes AutoCAD software, another large kind of major native desktop application, has already ported a version of their CAD software to the web using WebAssembly. So I think if anything, we might actually start seeing the real decline of native desktop applications with the advent of WebAssembly technology. And maybe in the future, everything is maybe going to live just on the web. Another implication is, again, there's no reason why JavaScript, the JavaScript language itself, can't see any of these performance gains, right? I wonder if maybe in the future whether it would make sense for browsers to even still be able to handle human written JS code, right? Like maybe it would just make a lot more sense to, and again, WebAssembly needs some additional features before we can really consider having JS code compiled to WebAssembly. But when that happens, would it actually make sense then for browsers to be able to still work with raw JavaScript, right? Maybe in the future, browsers will just be able to handle WebAssembly, and they can lop off the functionality to handle raw JavaScript, and then JavaScript would then just work in the browser by compiling straight to WebAssembly, and we'd see kind of all the same or most of the same kind of performance gains that we're seeing so far with comparing WebAssembly to JavaScript. But again, WebAssembly will need a garbage collector, and it'll need some way for to handle the fact that JavaScript doesn't have static types. But perhaps in the near future, we'll be able to see silly stuff like this. Maybe. All right, so let's talk a bit about, let's speculate a bit. That's really what this is. These are all next few slides are going to be all my own speculation. So disclaimer there. These are all my opinions. Well, what does the advent of WebAssembly actually mean for web developers? Well, certainly, I definitely think that the web is about to get a lot more interesting, and certainly, again, that goes back to the fact that when we were talking about a lot of native desktop a lot of applications that have historically just run as native desktop applications. I don't see any reason why those can all just not be migrated over to the web. So in the future, perhaps the web will just be the platform for all applications. Maybe we'll just see games running straight in the browser, like AAA PC games just running right in the browser. And maybe that would get rid of the whole, PC gaming versus Mac gaming debacle. I don't know. Again, I'm just speculating. Another thing is that JavaScript definitely isn't going anywhere. So you don't need to worry too much about that. Certainly, I think because JavaScript has so much maturity and tooling with regards to like working with the front end and stuff like that, it would take a long time for any other language that could be compiled to WebAssembly to kind of overtake JavaScript in that arena. So I certainly don't think JavaScript is going anywhere when it comes to doing what it's best at doing. So perhaps like front end manipulation and stuff like that. I think there will still be a use case and a niche for JavaScript. But perhaps, right, so one of the things I mentioned was that in order for JavaScript to see any wins from WebAssembly is that it needs some way to get around the type issue, and it needs a garbage collector. Garbage collection is something that is being worked on in WebAssembly, so that is going to be dropping in the future. The type thing, I'm not so sure about. I don't know what the plans are for that in the works at the moment. So if they decide that that's not something that they would want to add to WebAssembly, then another way that JavaScript could get around that is if everybody just moved to TypeScript, because TypeScript, of course, is basically JavaScript with types. And so you'd kind of be able to get around that particular hurdle. And in fact, there is a library already called assembly script that allows you to take TypeScript code and have it compiled to WebAssembly. But we still don't have garbage collection in WebAssembly for that, so it still definitely hasn't reached its full potential. So as far as assembly script goes, the people maintaining that particular library are waiting on garbage collection to arrive before that can really become a thing. And then lastly, I certainly do think that the number of tools and concepts and programming languages that web developers are expected to have under their belts will probably go up. I honestly have no idea if JavaScript will persist as like a backend language, because now there's languages that are much better at that entering the arena now. So I honestly have no idea on that front, on whether JavaScript will kind of persist as like a server-side language for doing backend stuff. I mean, perhaps working with, well, I don't even know. I don't even know what I would speculate for that. But certainly I think, right, we're going to see lower level systems languages entering the arena in the web context. And so I think developers are it's going to necessitate web developers being a lot more clued in on lower level computer science concepts and stuff that we already teach you guys, right? So which is great, right? So like you guys, Lambda School students, and because of the way we've structured the curriculum, you guys will certainly have a leg up over other like programming boot camps that just teach you web technologies, like just JavaScript or just Ruby on Rails, for example, because their curriculum is not, well, they don't talk about lower level systems languages like C, that you guys get exposed to. And so you already have seen a lot of the concepts that languages like Rust, C, and C++ kind of use in terms of their language paradigms. So you guys are less likely to kind of be blindsided, I guess, is my point. But yeah, that's it for the presentation. So now maybe I can go and catch up on and see what you guys have been typing in Slack. Oh, yeah, let me see. Yeah, she does some good work. Oh, Beach has been in here, okay. Kind of. Yeah, Beach probably did a good job explaining that. Well, don't know what that was in response to. TypeScript question mark. Oh, Vim, you don't know about TypeScript? You should look that up. A node can run WASM? I actually didn't know that. Is WebAssembly still run in V8? So yeah, basically all the major browser browser engines, yeah, they've all kind of been extended to be able to interpret and run WebAssembly as well. So yes, V8, which is Google's browser engine. Mozilla's is called SpiderMonkey. I forget the other ones. Safari obviously has one, and Microsoft Edge has one as well. I don't remember what they're called. Oh, in response to the memes. Okay. But yeah, all of those, all the major browser vendors are working on adding additional WebAssembly features as of now. Like WebAssembly, basically, MVP of WebAssembly was dropped, I think, end of 2017 in all of the major browsers. But at this point, there's still a lot of features that need to be added. So I know, for example, they're adding support for threading, adding a garbage collector, whole bunch of stuff that is on the horizon as far as features that are going to be dropping for WebAssembly. Y'all like the font? It looks like V has a built-in subsystem called Lift On. Okay. Oh, the previous slide. This one? Or I don't know which one you mean. Oh, interesting. Okay. Okay, interesting question. I don't. So that depends on what your React app is doing. So if it's like a simple, I don't know, obviously with like a to-do app or a notes app, I don't think you would do anything with that. Right? It's really for, like, again, I think most of the wins come from taking computationally heavy algorithms that right now perhaps live in JavaScript code, importing that to some other language using WASM. But I don't know if you had like, it's not a motivational slogan, more of a threat. I could see how you would spin it that way. I don't know. I guess it really depends, Ahmed, on what your application is doing. Um, Certainly, I don't think the React code itself would have to change, right? Because again, as I think JavaScript is still going to have a niche when it comes to rendering front ends and stuff like that. And I don't think anything like that would have to change. I don't know. It's kind of a hard question to answer. Let's optimize algorithm for convoys and run it in WASM. Compile language, some impact on performance. Then if you ran that same algorithm, that's the idea. Yes. So yeah, I do have a version of my implementation of life of Conway's life is in WASM with Rust. Bij's is in Go with WASM. But yeah, those are just kind of fun experiments that we ended up going with. So Bij likes Go more. I like Rust more. But anyways, there's no rivalry there at all. Oh, nice. I'm not really warming to Go. But I mean, for you guys, I think Go is probably a better choice as far as I want to learn. If you want to learn like a modern low level language, Go certainly has a much well, Rust's learning curve is a lot steeper. So I think for that reason alone, I think Go is probably a better candidate for a lot of you guys if you are interested in learning like a more modern low level language. I don't know about way easier to read and write. I think it's certainly easier to learn. Like I've been trying to learn Rust on and off for like a number of years, and it's yeah, it's takes a while to wrap your head around it. I understand Go to be more server type stuff and tools. Uh, I don't. Again, I don't know much about Go. Is there anything that would? I guess Beej would probably have a better answer to this. But is there any reason why you couldn't, for example, write an operating system in Go?
It would, well, a couple that I would recommend against doing such a thing. One is the garbage collector, probably one of the main things. Being not being able to do that. I mean, garbage collecting running at an operating system level, just I don't know. That freaks me out. It sounds like a bad idea. You don't want to wait for it ever. Uh, and yeah, I would think Rust would be way better for doing that lower level stuff in that regard. Go does have its concept of Go routines, which are super lightweight threads. And I'm not sure how they compare to what Rust has right now, but in Go, you can easily launch like 200,000 threads on a regular machine, and it won't complain about that at all. So it's if you want to write a server, Go's fantastic at doing that.
Hmm. I don't necessarily think that there are things you straight up could not do in Go that you could do in Rust and vice versa. It's just where the language's strengths lie, I guess, if that makes sense. So yeah, like they have kind of formed into they have found their respective niches. But again, I don't think that is to say that there's really anything in Go you couldn't do in Rust and anything in Rust you couldn't do in Go, I think.
They're both Turing complete, so in theory, we can do anything, right?
Fair enough.
And so is JavaScript. So hey,
Yeah, I don't. Again, you probably could you even write an operating system in JavaScript? Maybe.
You'd have to compile it to machine code.
Yeah. Cool. Are there any other questions, thoughts, concerns on anything we talked about this morning? Takes a minute or two to load. Oh, whoa.
According to Quora, somebody wrote an operating system in Java, which is a garbage collected language. So possible. So it's probably not as performant. I'll bet a Rust operating system is really performant. Plus, you get all those memory protections that Rust has that C doesn't have.
Yeah. That's the main win with Rust.
So, like, Linux doesn't crash very often, but it's a lot of that's been through like painstaking poring over code, making sure you're not dereferencing bad pointers and so on. Rust stops you at the compilation phase if you do that kind of stuff, which is kind of amazing. Wait.
What? Yo, what is this that's taking so long? What? Oh. Oh. That's cool, I guess. Oh, wow. Okay. Look at that. Yeah, I would honestly recommend any of the Mozilla blog posts related to WebAssembly. They write a lot of articles about it. So if it's something that you're interested in, I think pretty much all of their blog posts on the subject are pretty great. That's where I drew a lot of references, and the benchmark example that that I talked about is also from one of their blog posts. It's value too large. Cool. I guess I have a question for you guys, and that would be if anybody has anything they would like me to talk about for tomorrow's instructor hour, because I guess I didn't really have, I haven't come up with something yet for tomorrow. So I'm wondering if you guys had ideas you could throw out that I could consider. Talk about Rust. I could certainly talk you guys' ear off if you wanted that to happen. I feel like honestly the main problem with talking about Rust is I think you just a lot of the things that Rust is really good at, and a lot of the main wins that come with the language, just I feel like are just not really stuff you guys will care too much about yet, right? Um, right. So something that I've also encountered is like JavaScript versus TypeScript. It's like I think when you're first learning programming, I think JavaScript is probably initially the way to go, just because you don't have types in the syntax that kind of get in your way. Uh, Unlike in TypeScript, because then if you introduce like a beginner to programming in TypeScript and they're like, I got to write all these types out, it's taking me extra keystrokes. It's like I can see how that gets in the way of learning programming, right? I think it takes some time before the new programmer works with JavaScript more and really gets a feel for the fact that, oh, types are or if I had types here, it would allow me to not encounter this error that I'm seeing, or stuff like that. I think a lot of that kind of needs to be self-motivated by the learner, right? So I think when someone just introduces, I don't know much about those, but I think when if someone just throws TypeScript initially at a new programmer, they're not motivated to take on that extra cognitive load of writing types everywhere, or it doesn't make sense to them yet. I'm not saying I won't talk about Rust tomorrow. I certainly can. I just mean to say that I think a lot of the features that Rust introduces maybe are just not motivated yet for you guys. Yeah, sure. Okay, there's also comes with um I mean, really, what the double buffer is saying is nice. As far as the double buffer goes, pretty much what that means is you just have like you initialize two matrices in memory, and we're displaying one and we're writing to the other, and then we just flip those so that then the one that was just being written to is now the one being displayed, and we overwrite the data in the old one. We're working single buffer or double buffers, breaking everything.
Working with a single buffer? You mean like are we talking about the life state itself right now?
I think so, yeah.
Are you positive it's working is my first question, because uh, I don't know how to make it work with just one buffer. Actually, I kind of do, but it would be really painful compared to doing it with two. The idea is that one of them is the one that is built out that the user is looking at right now, and the other one is like a work buffer that you're building, you're constructing it. The user's not watching it while you're constructing it, while you're looping through, building the next generation of life. You're doing that like kind of off screen, right? And so you read from the current one and you write to the new one. And then after you're done writing the new one, you flip them. And the new one becomes the current one. Sort of like hiding all the dirty work of building out the next grid of life as you're building it. I don't know if that helps visualize it. The idea was originally from graphics, where you would show something on the screen to the user and you draw the next frame of graphics off screen, and then you pop that whole thing onto the screen when it was done being drawn. So if you imagine a complicated 3D scene, the user wouldn't see all these polygons popping into existence, because that would all happen off screen. And then when it was all done, bam, you show it to the user all at once. But that same concept of doing it on screen can be used within the game of life for doing the data juggling too. One of the buffers has the current state that's complete and the user's looking at. The other buffer is the one you're building.
I would guess if there's confusion, it's probably how to perform the buffer flip. Would be my guess. Is that kind of where the confusion is? Well, no, the canvas is just responsible for rendering whatever is the data type.
Yeah, I think I see.
Okay.
Yeah, what Sean was just saying, the canvas is sort of think of the canvas as the view onto the model. So we've got kind of three things here. We've got the canvas that is what the user is looking at, and then we've got two copies of the life array. So these are these three things. The two copies of the life array, those are the ones that are sort of the double buffer that bounces back and forth between reading from one and writing to the other, and then reading from this one and writing to the other one. But then also, in addition to doing that, you have a canvas that you take the currently completed life buffer and you draw that onto the canvas. So there's sort of three things going on here.
The buffers are just for figuring out the actual state of which cells are alive and which are dead. And then the canvas takes that and actually draws it all.
We're kind of touching on model view controller a little bit here, because we've got the model that's holding the data about which cells are on or off. And then we've got the view, which is this canvas that's looking into the data, that's separate from the data. So when I implemented this, I just have basically two arrays of integers, which are either ones or zeros, meaning the cell is alive or dead. And then I also had a canvas, and every frame I would loop through my array of cells which were alive or dead. And if it was alive, then I would draw the pixel white. And if it was dead, I would draw the pixel black. So one canvas, two buffers. And the buffers can just be regular arrays, yeah. Like I said, I just put ones and zeros in them. But the canvas, you've got to fill up with RGB values and all this other stuff. So every frame, I would iterate through my read buffer that was completed from the game of life, and I would translate that into colors.
Okay.
I think it's the easiest.
I mean, certainly with just if you just had a single array, like you would get some weird. The animations would look weird
Yeah, it
because you
wouldn't,
see the buffer being built up. I
because
mean,
you'd be modifying the same buffer that you were using to determine how many neighbors a cell had. So you'd be changing the cell's number of neighbors as you went, and it would make it strange.
yeah,
I think you could get away with not having a. How would you do this? I think you need to have like, if you didn't have a full double buffer, you could store just like the previous row. I think maybe, and then maybe the previous pixel to the. It would just be. I think it would be possible, but man, it
be
would
weird.
be a lot of juggling.
Right, you'd be mutating that buffer as you're also trying to render it at the same time. So maybe you could get away with. I don't know. I could maybe see something happening like if you just kept the canvas reading from the buffer right before it's getting mutated. I don't know. I could kind of see something like that happening, but well, maybe not. I don't know. Yeah, I'm not
It
sure.
might. We might also be able to think about this from like a pure data standpoint, where we have a data set A and we're using data set A to produce data set B. So data set B depends on data set A being a certain way. And this is exactly what we're doing with the double buffer, right? We take one buffer, data set A, and we use it to compute the second buffer, data set B. But because of that dependency, if we just used a single buffer, we would be modifying the same thing that we were reading from and kind of stepping on our own toes in that way. We would be, the act of writing the new data would be changing the data that it depends on. And that would corrupt it. It definitely does a thing, because the first time I implemented the game of life, I just used one buffer and it made like stuff happen, but it was not correct.
Yes, if you're doing it that way, where if you have a cell is 10 by 10 pixels, then yes, you would change the color of the whole of everything in there. Or is 10 by 10 your entire grid? I'm assuming you mean a single cell is 10 by 10, which I guess is fine. Right.
If you're using Canvas, I would recommend using the draw rectangle for that, because that's going to be way faster than manually going and
Yeah.
setting the individual pixels.
But image data also including the border pixels. I'm not sure what you mean by that. The border pixels, the pixels on the edge of the grid. So, yeah.
In my experiments with this kind of stuff, if you're just drawing single pixels, like 1 pixel per cell, then the whole get image data, put image data thing works faster. But if you're drawing bigger pixels, like 10 by 10 pixels, then drawing rectangles works faster.
Cool. I could certainly talk about Rust tomorrow. If that's what people want. I'd talk for a long time about that. All right, we're talking about Rust tomorrow.
Don's like, twist my arm. Okay, fine.
I'm not sure if I'm going to do it with a bunch of presentation slides. I don't think that would be the best format for that. I'll have to think about it, how I'd want to talk about it. All right, let's call it here. I should probably go eat some breakfast, but yeah. All right, thanks guys. I will talk to you all later then, and good luck.